So hi everyone. First of all, let me thank the organizer of this event. We all know how special these little encounters are, and in particular, I want to thank Professor Alfredo, who was very insistent for me to come here and show these things that he has seen a couple of years ago when I had my thesis defense. So, all right, so what I'm going to talk today is fermion dynamics with trajectory-guided Thouless determinants. So I'm going to explain what each of those things mean during the introduction here. But let me start by repeating something that Professor Grossman said in the beginning of his presentations, which can be stated more or less like this. There are mainly two reasons for studying this kind of thing, semiclassics. One, of course, is to understand better how does classical mechanics emerge from quantum mechanics, right? So every little bit of things here that we do in semiclassics helps us understand that. Personally, I think that's one of the most fascinating things in physics. But the second has to do with practical applications. So as Professor Grossman said, lots of semiclassical techniques are very good methods which produce very good results when applied to quantum problems which otherwise are very intractable to solve by a full quantum method. So I think I prefer to stand on this side here. All right. So let me start by explaining what are these trajectory-guided or trajectory-based methods. So our purpose here is to solve the so we want to do quantum dynamics. So we have to solve somehow the time-dependent Schrödinger equation. And that's that equation there. How would you do that the standard way of doing that, the traditional way? You start by expanding your wave function in some set of basis functions here, and you have some time-dependent amplitudes. And if you plug that into the Schrödinger equation, you have to solve these equations, a matrix-like equation for the amplitudes. And the basis functions are not necessarily orthonormal, all right? However, there are some types of problems that, you are going to waste a lot of effort trying to solve in that way. So let me exemplify this. Never mind the details of this system. I just want to emphasize one point here. So, but to give you some physical background, this has to do with some model for describing the interacting bosonic particles in a double well. So it's approximate model for that dynamics, for that system. And as it turns out, the state of that system can be represented in the Bloch sphere. All right? All right, so that's a Bose-Einstein condensate. So all particles there are occupying a very specific state. So it's a very localized distribution in this representation. And well, this is at time equals 0. What happens when you start solving the Schrödinger equation? That thing is going to move. And the point here is that it changes a lot and everything, and kind of a little mess there, but it never goes into all other parts here of the sphere. So let me just roll. So something interesting happened here is a recombination of the Bose-Einstein condensate. But the point I want to emphasize here is that if you're solving the Schrödinger equation using that basis functions, and each point of this sphere could be assigned, could represent one of those basis functions, the amplitude for most of them would be 0, almost during the entire dynamics. So there will be a lot of wasted effort there. And the idea of using a time-dependent basis is motivated by that, in order to not to waste so much effort in doing that. So the idea is like this. Instead of using the full representation, you only need a grid of basis functions initially distributed where the state is localized, and you would assign some type of dynamics for this. So each point here represents one of the basis functions, and they will move around and kind of follow the dynamics of the wave packet. And then you, instead of dealing with the entire sphere there, you would only need to solve the amplitudes for those points. All right, so the question here is how to assign that dynamics. How do you choose how the basis functions move? I will start referring to these basis functions as configurations, since each one of them is a possible state of the system. All right, so that's the wave function. Now, the amplitude equation is always the same. So it's similar to the last one I showed, but it has some, extra terms there, which are due to the time dependence of the basis functions. And what's the best way to evolve this configuration? So maybe the first thing that you think of is to use the time-dependent variation principle. So the time-dependent variation principle will give you an answer for that question. You can find the trajectories. I'll call trajectories. I'll call these dynamics trajectories of each basis functions by doing some minimization through the time-dependent variation principle. All right, so this leads to so-called full variational methods, meaning that, and I'm here writing this in a very broad way, very general way. So if each configuration, I guess this one? No. All right. Each configuration is parameterized by a set of parameters, which I'm calling C here. So it's a vector of parameters. You can find an equation, equation of motion for each one of those C. And it will have this general form. So what I want to emphasize here is that this is very complicated. So in fact, you have all of the parameters for all configurations are coupled together, including a coupling with the amplitude, all of the amplitudes. So this dynamics is very complicated. Still, there are plenty of methods which are based on this type of wave function. I'm going to mention just a few of them just to, well, it's basically the family of MCTDH methods, which stands for multi-configurational time-dependent Hartree methods. So, for instance, in this standard multi-configuration time-dependent Hartree method, each configuration is actually a Hartree, hence the name, right? A Hartree product of single particle basis functions. So here we are looking at a system with n particles, and each one of those may be written as some linear combination of primitive functions. And here are the parameters that parameterize each of that configurations, which are the ones that you have to evolve in time. There's also the bosonic and fermionic versions of that method, which you take symmetrized or anti-symmetrized products. And also a version of that method based on Gaussian wave packets. All right, so each configuration now is a multidimensional Gaussian wave packet. A Gaussian wave packet is a Gaussian centered at some position and momentum. All right, now let me see, some points to be made here. So as I told you earlier, the dynamics for these configuration parameters in a full variation approach is very complicated. So these trajectories, let me use this example because it's very familiar for all of us. The dynamics of this coordinate momentum variables will not be, the classical dynamics we are used to. It will be some very weird thing, and that's a bit. You kind of lose something there, I think. It's mostly a matter of opinion, but if these trajectories were classical, then you can really interpret each contribution from each classical trajectory. But if you have something weird, all right, you will solve the problem, but maybe you cannot interpret it just as nicely as you would if you had a classical picture. All right, so let me just list some properties of these methods, and this will serve as the motivation for the things I'm going to present next. So, as I told you, earlier, these methods, by employing these time-dependent basis functions, they are able to solve problems which are otherwise untractable with fixed basis functions. So they are suitable for multidimensional problems. So the MCTDH family of methods are, there are lots of benchmark problems for multidimensional systems with very accurate results. So they have a systematic convergence, meaning that as you add more basis functions, they will eventually converge to the exact answer. And therefore, they are reliable. All right. On the other hand, they are computationally expensive, as you may figure. It's computationally cheaper than doing the standard quantum treatment based on fixed basis sets. But they are still very expensive. And still a lot of effort is wasted for some types of problems. Now, like the one I showed you in the beginning, right? Because I'm going to explain this better later. And there is another point here. I think it's a bit maybe controversial, but I think that a large basis set that you need in order to converge the solution kind of defeats the purpose of the time-dependent variational principle. What I mean here is that, you can actually make a little calculation and demonstrate this. As the basis gets larger, it will eventually get complete. So think about that sphere again. You are filling up all the sphere, and then you are sure that you have the entire description of the quantum system. But as you reach that level of description, the dynamics, the underlying dynamics of each basis functions becomes irrelevant. So you can, it's kind of intuitive, right? So if you have a large enough basis, the basis set doesn't matter how you tell the trajectories to move around. All right. So what I want to talk about, the so-called trajectory-guided approach, so I'm going to talk here, they are kind of a intermediate thing. So, all right, you still have a wave function expressed as a combination of many time-dependent configurations. Each has an amplitude, which will still obey that equation. However, instead of looking for a variational equation for the basis functions, you simply assign dynamics for these basis functions based on some other motivations. In this case, for instance, in this problem, so already kind of saying some of the things I'm going to say later. Classical trajectories are assigned for this system. But here it's not the usual key coordinate momentum space, but rather a trajectory on the block sphere. So this is how these initial conditions here evolve on the block sphere. So they describe these trajectories here. And you certainly notice that most of the trajectories, they stay in this region where the wave function moves, right? All right, and that actually gives a very good description of the quantum problem. That's some previous work there. All right. So there is a method for that, which simulates these ideas, and is being around since the early 2000s. I think many people here know about it. Professor Grossman mentioned it in his presentation, which is the CCS method. It stands for coupled coherent states, and here the coherent state is a Gaussian. So it's a method where you write your wave function as a combination of Gaussian wave packets. Each wave packet has this position representation here, and you ascribe classical dynamics for the parameters of each Gaussian. So they're frozen Gaussians. They will move around in phase space, and you solve that amplitude equation to get the quantum results. All right, so let me show some more things here. So what's the energy function here, the Hamiltonian that is governing the dynamics of the trajectories? It's the Q symbol Hamiltonian, which is the mean value on this sets of states, the Gaussian functions. And it will usually have this form here. So if you have a Hamiltonian which is originally written in terms of x and p operators, that the e appearing here will be this function here, some function like this. And there's a thing here, so it moves out, so because you're averaging on Gaussian wave functions, you actually have a smoother potential here. Just a minor detail. All right. And that phase there is there for a very good reason. So that's the action phase, and it's the action is responsible for subtracting most of the time dependence of the overall amplitude here. So rapid oscillations in the amplitude are described by the action. What I mean is that the evolution of this amplitude d here is not so fast varying as the overall amplitude there. But actually, that's not quite true. I will explain why later. But just keep that in mind for a bit. All right. So this kind of summarized the CCS method. And all right, how well does it perform? So there's a lot of papers, mostly from the Leeds group with Professor Dimitri Shalashlin, which applied this kind of wave function ansatz to all kinds of problems in a molecular context. So in a molecular context, you use Gaussian wave packets in order to describe the motion of the nuclei. So that's a very, very ideal system to introduce semi-classical types or trajectory-based methods like this. And you can actually treat very large dimensional systems. And here I'm showing some papers, but only to illustrate the applications and to establish that this method has been proved, has been successful. And there are some evolutions of it. So this is the multi-configuration Ehrenfest method, where you have electronic degrees of electronic potential energy surfaces coupled to the nuclei degree of freedom, and this kind of cloning algorithm, which is designed for treating non-adiabatic dynamics and changes in the, when the system changes electronic surfaces in molecules, and a two-layer thing, which is kind of a complication of that method. All right. So the method I'm going to talk about today has a great similarity. Actually, is completely inspired in the CCS method. It's a generalization of the CCS method. So I want to tell you about some of lessons from that, which I'm going to call here Gaussian-based CCS method. So as I told you, it has been successfully applied to systems with 7 degrees of freedom. And the results, most of the time, are comparable to benchmark MCT-DH calculation, which are far more expensive calculations, all right? However, there are some observations to be made here. These results are mostly obtained for systems which already have a very prominent semi-classical character. So this method, although in principle you can use it for any quantum system, it's not designed for that. So the fact that your basis functions are evolving according to classical dynamics kind of makes the method appropriate only for systems which have that kind of behavior, more or less. The fact that this trajectory is moving a classical phase space is important. So I mean this classical phase space like having the properties of classical dynamics. So the dynamics is Hamiltonian, you have Liouville theorem satisfied, so conservation of volumes and all those kinds of things. And also related to that, the identification of Gaussian wave packets as coherent states is key. So as we know, Gaussian wave packets are position representations of harmonic oscillators coherent states, which have some importance in quantum optics. And they are not, this kind of method, it's not expected to remain accurate after a very long propagation time. All right, and it's not expected, but that's okay, because in the end what we want is to have the dynamics accurate only for a sufficiently long time so we can calculate decent autocorrelation functions and other kinds of observables, and Fourier transform, get a spectrum, and something like that. All right, so they really don't need to be accurate for extraordinarily long propagation times. Okay. All right. Now I come to the subject of this talk, and it's basically motivated by two questions. So, can we expect similar results if other types of configurations are evolved? And by that I mean, in particular, if I can, using this identification of the Gaussian wave packets as coherent states, it's easy to wonder if I use other types of coherent states to do these types of propagations, would that work too? And other types of coherent states include coherent states capable of describing systems of indistinguishable parts, such as bosons and fermions, right? So, that's one thing I have to say. Everything I'm going to show applies for all kinds of all coherent states, all types. So, well, Lie group coherent states, but I'll be mostly focusing on fermionic coherent states. And well, there was a first step on that direction in an old paper here some time ago, where we proposed this generalized coherent state propagation strategy, and we have a proof of concept for a bosonic system. So those earlier images I showed you are just leftover images from that work. And this is kind of a preview of the things I'm going to show today. During my PhD, we did that same kind of proof of concept for fermionic systems. So we have come a long way since that 2016 work. So we have improved the bosonic results as well, and we have established that this fermionic thing with the fermionic coherent states works as well. All right. I guess that's what I have to say here. A quick note. So, of course, there has been previous works which attempted to do this kind of method with specifically for fermion dynamics. So that's a very interesting thing in the quantum chemistry area. So one of them is this work which uses, instead of Gaussian functions, anti-symmetrized Gaussian functions, which is very interesting. So it's more like a mechanistic description of electronic motions. And more recently, last year, Professor Shalashkin came up with this funny thing, which are the zombie states, which are a kind of fermionic parametrization, which I'm not sure I understand well yet, but it's very interesting. All right. So for the remainder of this talk, I'm going to talk about the fermionic parametrization I'm going to use on the CCS method, which is called the Thouless parametrization. I will present the working equations of the method, show the results to a model system, and finish with some remarks on a semiclassical formulas which can be derived from this method. So, all right. So I'm gonna spend some time here because maybe not all people here are familiar with Thouless determinants. So, but maybe you have heard about Slater determinants, right? Slater determinants are wave functions, types of wave functions used to describe fermionic systems. So they automatically incorporate the Pauli principle. And we all know, right? So if you have n particles, you say that each particle is occupying one orbital, spin orbital, whatever, and you set up a wave function which has this determinantal form. So, of course, this is an approximation for the fermionic system, a single determinant will not describe completely a fermionic system. In general, you need to make a combination of many determinants. But the Thouless determinant is so one way to perceive the Thouless determinant is to look at this later determinant and remove all the redundant parameters on this later determinants. All right. So I want to do that here, but I need to introduce some abbreviations of notation just to not to be too messy. So I'll write the determinant like so. This I can write like this. I think this is pretty obvious what it means, and I will further write it like this. So you kind of have to see this as a matrix thing. So the rows and columns, right? So I'm gonna use that just to make it easier. So what are these redundant parameters I'm talking about? So if you take those occupied orbitals of the determinant and you make a linear transformation, you end up with a determinant, which is later determinant, which describes precisely the same physical situation, the same system. Because if you substitute that transformation here, you get this kind of matrix multiplication inside the determinant, and the determinant of the product of matrices is just the product of the determinants. It means that this state and the resulting state here are related by a simple constant, and so they are the same physical state. Meaning that you have some kind of freedom here to choose a particular representation by controlling these transformations, right? So I'm going to use that to get rid of the redundant parameters. And to do that, I'm going to introduce now, so far I've been talking about Slater determinants, but I'm not referring to any specific physical problem. In order to do that, I have to specify single particle basis functions. Think about the hydrogen atom orbitals, right? So you have to write each state of each electron in terms of some combination of hydrogen orbitals, something like that. This is exactly what I said now. So each orbital will be written as a linear combination of these basis orbitals. In matrix terms, I write it like this. So I have k orbitals, which is larger than n, because you always have to have more orbitals than electrons. And this is kind of a rectangular matrix here, which are these coefficients organizing the matrix. So let me explain this. 1 refers to occupied space, and 2 refers to unoccupied or virtual space. So that's why 1, 1, and 2, 1. And so you write this later determinant in terms of single particle basis functions like this. So these are the parameters of this later determinant. And as we know, they are redundant because of this physical equivalence between the states. So this determinant here is equivalent to this one. All right? So, and I like to think this is a kind of gauge fixing analogy. So you have this matrix here, and you can choose it whatever you like in order to describe the system. So you choose it to be the inverse of the first block there. And then you end up with something like this. So because of this choice, the first block here is going to be an identity, and you end up with an effective set of parameters here called Z, all right, which are the Thouless parameters of the determinant parameterization here. And that's it. That's the Thouless determinant. And so it's this kind of parameterization here where you have removed some of the redundant parameters, and yeah, that's it. So one thing I forgot to explain, like the bullet symbol here means occupied space, and the empty symbol here, the virtual space. All right, that's the position representation of the Thouless determinant. So I presented here a very, physically motivated thing, construction of the Thouless determinant, but actually it's actually that parameterization is actually a coherent state. It's a Lie group coherent state, and it's if you write it in second quantization form, you end up with this expression here. And these are the fermionic coherent states of the SU, in this case SUK special unitary group, Lie group. And you see here I have the whole family of groups of coherent states of the, let me show here. So all of them have the same structure. So let me start first describing this one. I think this is the most familiar for all of you, is the harmonic oscillator coherent state. So here you have the vacuum state, and you know this is the displacement of operator parameterized by some complex numbers here. And we know that is the state which evolves coherently in a harmonic rotation. So it's written in terms of bosonic operators. Likewise, you have a bosonic type of coherent state. This is the coherent state for a set of n bosonic particles evolving, which may occupy k single particle orbitals. These are the states that I showed in the beginning, but for k equals 2. And n is just a parameter here. And these are the fermionic states that are the Thouless states. So you see there's a nice similarity here. All of them have this structure where you have a reference state. Here is the vacuum state. Here is the state where all n bosons are occupying the same mode. And here is some specific Slater determinant. 5 minutes. Oh, this goes very fast. Eh? So the idea is, how does Z evolve from initial conditions? So I'll go fast now. So if you have a Hamiltonian, a second written in this form here, so with one and two body interactions, the equation of motion which follow from the time-dependent variation of prism applied to a coherent state, to the Thouless state, have this form. So, you know, some important matrices here. This is the Fock matrix, and this is the one density matrix, which tells how the fermions are distributed in the single particle orbitals. I would mention this is some other work that uses this same kind of states. These are the workings equations of the CCS method based on Thouless determinants. All right, so instead of writing the equations for the D amplitude, you use a well-behaved amplitude, which is the C amplitude. That's why I said in the beginning about it. And that's it. These are the equations of the method. All right, so I'm gonna just show the form of the matrices appearing here. I'm not going to go into details here. This is the coupling matrix. This is the important matrix, which tells basically how different amplitudes are coupled with each other. And the problem I'm going to show the results here is this Hubbard chain problem, where you have a Hubbard model describing electrons moving in a ring. All right, so I don't think I'm going to go into the details here. I think the Hamiltonian is here, so it's the thing here is that it has a magnetic field as well. The reason for the magnetic field is just to make the spectrum a little bit more rich. I'm not going to these details of the reciprocal representation. All right, so I'm going to solve this problem using the methodology I just laid out. The initial state will be a random state, which is close to the unperturbed ground state, all right, including the magnetic field. And yes, I think that's enough to know. And the basis set, so the configurations are sampled around the reference state, which is in turn close to the initial state, because the initial state is a random state close to the reference state. And I'm going to calculate autocorrelation functions and the populations of the tight binding levels, the unperturbed levels of that system. And the goal is that these quantities will match the quantum results, fully quantum results. So here, just a diagnosis. The energy is not exactly conserved, because that usually is not for a trajectory guided method. But the results for populations are very are very close to the exact quantum results. So here you have the populations of each of the levels, and they match quite well the evolution of the quantum state. So let me just mention that these are very highly dimensional systems. So you have here 27 degrees of freedom on the phase space. And I can get these results with just 170 trajectories on the base set. This is the autocorrelation function, so it matches very well. By the way, this is the 6-site ring, right, with 3 electrons. The spectrum, compare with the exact spectrum. All right, I'm not going to talk about this, unfortunately. And some larger systems now. 9 sites. So the point here is to show that it matches the quantum results. And 10 sites, all right, so, and, all right. Some conclusions here. So maybe if you want to know about this, you can ask me later. I know it's very late and we are all tired from previous presentations. All right. Here's, I'll just make a very fast note here. So if you compare the results obtained with the CCS with the results obtained with a single base set evolution, which would be kind of equivalent to a time-dependent Hartree-Fock calculation, you see that you can actually get this beyond mean field effects, right? So a Hartree-Fock calculation will not get the exact populations. And, you know, just like you can derive Hermann-Klug propagator from the CCS formula, you can also do the same calculation here, of course a bit more complicated in the math because of the geometry of these states, to get a semiclassical propagator which has the same structure of the Hermann-Klug propagator, but now it works with this time-dependent determinantal states. Right, that's it. Thank you. Some acknowledged here. And thanks. Sorry about the time. Oh, yeah.
We have a little bit time for questions.
All right.
So it was a really very nice talk and very interesting results. I wanted to ask about what you mentioned.